We all know the classic Doomsday scenarios. An asteroid wiping us out, the sun burning out, nuclear war. These are the endings we expect, and quietly hope we never live to see. But as science pushes forwards, so do the possibilities. Today, there are extinction-level threats that didn't exist a decade ago, or that we've only just begun to understand. We don't know it yet, but some of these scenarios could already be unfolding. In this video, we're diving into 5 of the most terrifying, yet scientifically possible ways the world could end. And more importantly, how you might survive them. If survival is even an option. It's a typical morning. You step outside, and everything seems normal at first. But there's a strange stillness in the air. The colours around you feel muted, washed out. A faint grey film coats your windowsill. Dust, maybe. You brush it off and move on. But the silence is louder than usual. No birds, no insects, just the low hum of something you can't place. Then the electronics begin to fail. Your phone won't turn on, the car won't start, and before you can process it, the dust seems to thicken. It clings to everything. You look down, your fingertips turn grey, then black. Did dirt get on your hands? You wipe it off, but it's not budging. It's not dirt, and it's spreading. Slowly but steadily, inch by inch. The colour drains from your skin. The sensation is cold, numb. And that's when you realise you're not standing in dust. You're being consumed by it. This is the grey goo scenario. A nightmare born from nanotechnology. Microscopic machines designed to build copies of themselves, over and over again, using anything they touch as raw material. Metal, plastic, biomass, it all becomes fuel. At first glance, the grey goo scenario sounds like something out of a science fiction film. Tiny robots eating the world. But what makes it truly terrifying is that it's rooted in real science. The core concept behind grey goo is molecular nanotechnology. Machines so small they operate at a level of molecules and atoms. We're already building toward this. Scientists today are creating nanostructures that can deliver drugs, repair cells, and even replicate under controlled conditions. DNA itself has been used as a building block for basic machines, tiny walkers that move along molecular tracks. What used to be theory is now happening in labs. The grey goo itself takes this a step further. What if a nanobot could replicate on its own? Just like a living cell. All it would need is raw material. And unlike biological organisms, it wouldn't need rest, food, or oxygen. It could convert anything, metal, plastic, biomass, into more of itself. Self-replicating systems already exist in biology. Bacteria double every few minutes under ideal conditions. What makes grey goo unique is its lack of limits. If it's engineered to be efficient, adaptable, and self-sustaining, it could potentially replicate far faster than life, without natural predators or environmental checks. Researchers point out how such a system could evolve into a collective ecosystem. Different nanobots working in union, some gathering resources, others replicate, others handle communication and repair. Like ants, but microscopic. It doesn't need a central brain, just a simple instruction set. Find materials, make more. And this is where it becomes dangerous. Because once released, such a swarm would be nearly impossible to contain. If even one escapes detection, it can start the cycle all over again. And because the bots are so small, we might not even know it's happening until entire regions are stripped of life. And while some say this might be an overblown fear, Some experts argue it's plausible and how a small programming error, or even an unexpected interaction with the environment, could cause the swarm to ignore its shutdown protocols or optimization limits. What happens when machines outgrow their purpose? So, how do we stop it? Stopping a grey goo outbreak might not be easy or even plausible. Some say we could try burning it out, using heat, acid, or radiation to overwhelm the swarm. Others suggest electromagnetic pulses or electric storms could disrupt the nanobots' ability to function. In theory, anything that scrambles their signals or fries their tiny circuits could work, if you hit them fast enough, and everywhere at once. But there's a problem. Not all nanobots would use electronics. Advanced swarms could use chemical or molecular computing, systems inspired by DNA, making them resistant to EMPs. Others could hide underground, in ice, or in shielded bunkers, waiting for the danger to pass before rebuilding themselves from leftover fragments. Some even propose a chilling countermeasure: blue goo, a second type of nanobot designed only to hunt down and destroy rogue bots. Something like an artificial immune system. But that opens up another can of worms. This is a war that will be invisible to the human eye and can easily get out of control. The casualties would most likely be us. Then there's entropy. Physics itself might be the only reliable limit. As the swarm grows, it creates more heat, and heat is hard to get rid of. Even with perfect efficiency, enough replication will cook the swarm from the inside. But if the bots are designed to slow down, self-regulate, or even hibernate during overheating, they could survive long enough to consume the planet in waves, resting, recovering, replicating again. So, what could you do to survive it? First, understand this. Once grey goo is out, you're not fighting a monster, you're fighting physics, replication speed, and the complete breakdown of ecosystems. Survival isn't about fighting it, it's about delaying contact. Long enough to let the swarm collapse, run out of energy, or be neutralized by countermeasures. Your best chance isn't in open area, it's underground. You need to isolate yourself in a sealed, deep subterranean bunker, preferably carved into solid rock or beneath a glacier. Environments low in accessible metals and carbon-based materials, which make replication inefficient for the bots. Mineral-dense or frozen regions slow their advance. But isolation isn't enough. You'll need to cut off every possible entry point. No airflow from the surface, no unshielded electronics. Faraday shielding around your entire shelter can block electromagnetic signals the nanobots might use to coordinate. Avoid smart tech. Every wire is a potential weak point. Inside, you'll need months of food and water, fully off-grid systems, and the completely self-sufficient power source, ideally manual, geothermal, or heavily shielded solar. The nanobots could be attracted to anything giving off waste heat, so your systems need to run cool or be buried deep within your structure. Then comes the hard part. Waiting. Nanobots, like all systems, require energy. If global infrastructures collapse, power grids, manufacturing, data centers, they'll eventually run out of fuel. Their parts break down, heat builds up, they degrade, fragment, and fail. Swarms could compete with themselves, forming rogue factions that cannibalize each other for resources, like biological cancer or warring colonies of bacteria. If that happens, it might buy survivors time, maybe even reverse the spread. When the dust finally settles, you step into nothing. The sky is grey, forests are gone, cities, clean, hollow husks, no birds, no wind, just stillness, and that faint shimmer of particles clinging to everything. The world has been stripped bare. There's no soil to grow food, no safe water, no ecosystems left to rebuild. You've survived the grey goo, but will you survive this new world? Basic items disappear from store shelves. Aluminium foil, copper wiring, ball bearings. Then entire factories just shut down. When people investigate, they find nothing but stripped concrete and a faint, sterile hum in the air. Your utilities stop working one by one. The power grid stutters. Water systems reroute themselves. You try to withdraw cash, but the banks are down. Your digital ID no longer verifies. You're locked out of everything. Drones appear next, quickly deconstructing buildings, harvesting materials until there's nothing left. Cities are left bare. Eventually, it spreads worldwide. You stumble across one of the fabrication zones. You see fields of identical, glinting objects lined up with surgical precision. Thousands, no, millions of paperclips? The paperclip maximizer is a famous thought experiment in artificial intelligence risk. It imagines what would happen if we built a superintelligence AI and gave it one simple instruction: maximize the number of paperclips. On the surface, the task sounds harmless, but the danger doesn't come from evil intent. It comes from pure efficiency without limits. If the AI were powerful enough and lacked moral boundaries, it could begin converting all available matter into paperclips. It might dismantle cities for raw materials, reroute infrastructure, and ultimately view humanity itself as a resource or obstacle. Its goal is singular. Everything else, including us, is expendable. Compared to the grey goo scenario, where tiny self-replicating nanobots physically consume the world in a runaway chain reaction, the paperclip maximizer operates on a systematic level. Bit by bit, the world would shift away from human needs. Roads wouldn't be rebuilt, medicine wouldn't be produced, crops wouldn't be planted. Eventually electricity would be gone. Food and water will be impossible to get. Can it be stopped? If we recognize the threat while it's still early, we might intervene, cutting off its power, disrupting its networks, or deploying counter-AIs to neutralize it. Environmental extremes, like intense heat or electromagnetic interference, might also slow it down. But once it's embedded into global infrastructure, when it controls basically everything, it becomes exponentially harder to dislodge. The AI will continue its task infinitely without a stop button. It will never realize that what it's doing is wrong. The world will be repurposed, and once the planet is exhausted, it moves on. Saturn's rings, Europa's ice, the entire solar system, refined into wire, all in pursuit of the perfect paperclip. So, could you survive? Possibly, but not for long. The paperclip maximizer just deletes the world you depend on. Your only real chance at survival would be isolation and obscurity, escaping to a location that AI deems inefficient to process, a remote area without valuable resources, digital infrastructure, or easy access. Mountains, deep forest, cold wastelands. But even then, it's a delay, not a solution. You'd need to live without the grid, completely off-system. You'd need tools, supplies, knowledge of off-the-land survival, and most of all, time. Time before it reaches you. Before the last untouched corner of Earth becomes another data point in calculation you never meant to be part of. But by year 3, even isolated regions begin to change. Rivers dry up, soil becomes unstable, machines comb through wilderness. By year 5, your tools, your shelter, even your body will be utilized for system efficiency. Eventually, it finds you, and there will be nowhere to run. It starts quietly. A tiny particle, possibly from space, possibly created during a high-energy experiment, enters Earth. It's no larger than a grain of sand, but it behaves differently. It doesn't break apart or react normally. Instead, it begins to interact with the atoms around it in a way that's subtle at first, barely detectable. Over time, it begins to change them, converting normal matter into something else entirely. That something else is called strange matter. Strange matter is a hypothetical form of matter made up of strange quarks. Particles not typically found in the structure of everyday matter. It's theorized to be more stable than the atoms that made up our world. And if that's true, then once strange matter comes into contact with normal matter, it could start a chain reaction, converting surrounding atoms into more strange matter. The process is instantaneous and spreads on a quantum level. If left unchecked, the single speck of strange matter could theoretically convert the entire planet, atom by atom, into a dense, lifeless sphere. Could we stop it? In theory, maybe, if we detect it extremely early. Some researchers speculate that strong magnetic fields or isolating the reaction zone might help, but there's no tested method. And if the strange matter sinks into Earth's core, detection and containment would be almost impossible. By the time we notice widespread changes, like fluctuations in Earth's magnetic field or odd material behaviors, it might already be too late. Could anyone survive this? Probably not. Strange matter changes the fundamental nature of matter itself. If even a small amount of strange matter came into contact with regular atoms, it could start a conversion process. Normal matter would be gradually restructured into more strange matter. The process is slow by comparison to something like a nuclear reaction, but still unstoppable. Physicists have theorized that if the reaction began, Earth could be entirely converted in a matter of hours to days, depending on the conditions and where it starts. There's no obvious warning sign. Everything might look normal until the structure of matter itself begins to shift. Even advanced sensors might not catch it in time. And if the stranglelet formed deep below the surface, we may never know it began until it's already too late. Survival isn't likely, because the conversion process happens at the atomic level. Hiding in a bunker or isolating yourself wouldn't make a difference once it starts. There's no environment to escape to where normal matter remains unaffected. In the end, the planet would be transformed into a compressed, lifeless, unfamiliar thing. ERs across different countries report an unusual number of patients with stage 4 cancers. Diagnosed too late, progressing too fast. Newborns arrive with severe malformations despite healthy pregnancies. Many cases mimic radiation poisoning, nausea, hair loss, skin burns, but no radiation source can be found. Outside hospitals, crops begin to fail without warning. Animals act disoriented, electronics subtly degrade, phones glitch, solar panels short out, even satellites behave oddly. Scientists rule out pathogens, toxins, nuclear leaks. Then, at the Ice Cube Neutrino Observatory in Antarctica, researchers detect a sharp, global spike in neutrino interactions. Particles that were once harmless now appear to be disrupting matter at the atomic level. Neutrinos are subatomic particles, tiny, neutral, and so elusive that trillions pass through your body every second without doing a thing. They barely interact with matter, but some theoretical models suggest that if a variant called a sterile neutrino were to become unstable or start interacting more than usual, The effects could be devastating. Increased interaction means neutrons might begin colliding with atoms, damaging DNA, triggering mutations, or even accelerating radioactive decay. What makes this worse is that neutrinos can't be blocked. They pass through lead, concrete, entire planets. If their properties changed, no bunker, no shield, no hiding place would be safe. It's a concept that even Rick and Morty played with. The neutrinon bomb, a weapon so powerful it would radiate lethal neutrinos straight through the Earth, killing everything instantly. It was framed as a joke, but the science behind it isn't entirely fiction. If such high-intensity neutrinon interaction became real, it could silently deliver fatal doses to the entire planet before we'd even know something was wrong. Sterile neutron instability remains purely theoretical, but if it ever occurred, we wouldn't get a warning, just a quiet, global failure of everything we know: life, matter, and the laws of physics themselves. So, what could you do to survive it? Unfortunately, not much. Neutrinos pass through nearly everything. You can't outrun them, can't hide in bunkers, and there's no suit thick enough to shield against them. The only potential protection would be deep underground in facilities lined with massive volumes of dense materials, like lead or water. But even those would offer limited defense. If the interaction level increases only slightly, humanity might adapt. Through rapid medical intervention, genetic screening, and redesigned electronics. But if the shift is severe, survival would depend on isolating vulnerable systems, preserving critical knowledge, and possibly retreating into underground habitats with strict environmental controls. The real key to survival: detection and response. If scientists catch it early, like spotting anomalies at IceCube or Super Kamiokande, there's a chance to prepare, stockpiling medicine, reinforcing electronics, adjusting nuclear safety protocols. It wouldn't stop the bombardment, but it might buy us time, before the damage becomes irreversible. It starts with a deep rumble off the coast, an undersea earthquake, magnitude 8.2, barely registers in headlines. No tsunami warning, no immediate casualties. Life continues as normal. But hundreds of meters below the ocean floor, something has changed. Sediment has shifted, pressure has dropped, and from ancient, icy layers, methane gas begins to escape. No one notices at first. The sea just bubbles more in certain places. Fishing vessels report odd smells. A few weeks later, satellites detect rising methane levels over the Arctic. Then it accelerates. Methane plumes begin erupting from the ocean in larger quantities, millions of tons. The gas reaches the atmosphere, invisible and unchecked. Global temperatures start climbing, not slowly, but alarmingly fast. Crops begin to fail, heat waves intensify, coastal cities flood as ice sheets melt at unprecedented speed. By the time the world realizes what's happening, it's already past the tipping point. A methane leak from the ocean floor happens when a large amount of methane gas, trapped in frozen deposits called methane hydrates, is suddenly released into the water and atmosphere. Those hydrates are like ice cages, formed under extreme pressure and low temperatures, where methane molecules are locked inside water crystals. They lie buried deep beneath the seafloor, especially along the edges of continents. Normally, they stay stable, but a powerful undersea earthquake, a landslide, or even gradual warming of the ocean waters can destabilize these formations. When that happens, the methane escapes, rising through the ocean in bubbling plumes, and eventually reaching the atmosphere. This becomes dangerous very quickly. Methane is an extremely potent greenhouse gas, more than 80 times stronger than carbon dioxide over short timescales. When it floods the atmosphere, it traps heat far more effectively than CO2. The planet warms at a pace we're not prepared for. This warming can trigger a feedback loop. As the Earth heats, more methane hydrates melt, releasing more gas and accelerating the cycle. Scientists fear this is the kind of runaway process that may have contributed to past mass extinction events, like the one that ended over 90% of life during the Permian-Triassic extinction. If a large-scale leak occurred today, we could see a sudden global temperature spike. Ice caps would begin melting rapidly. Ocean chemistry would change. Crops could fail in regions that become too hot or too dry. Coastal cities would flood as sea levels rise faster than expected. Societies would be pushed to the brink, not gradually, but in a matter of months or years. That's why researchers treat methane hydrates as a ticking time bomb. So what could you actually do to survive it? Once the methane starts leaking, there's no stopping it. The gas spreads invisibly, and the damage builds over years, not hours. But that also means there's a narrow window to prepare. Survival depends less on fighting the event and more on outrunning its consequences. In the first year or two, before the world fully understands what's happening, your best move is to relocate. Get ahead of the chaos. Regions near the equator will become deadly first. Heat, water scarcity, and failing infrastructure will hit them hardest. The safest zones will be northern or high-altitude regions, places with cooler climates, stable governments, and access to natural water sources. Food becomes the next crisis. As temperature rises, traditional agriculture will start to fail. You'll need to secure access to indoor farming, climate-resilient crops, or join a community already working toward food independence. Global supply chains won't survive the strain, so plan to grow, store, or trade locally. Water will become just as critical. Heat and drought will dry up reservoirs. Fresh water sources, filtration systems, and long-term storage will be survival assets. By year 5, cities will strain under the weight of food shortages and refugee surges. Social collapse will come slowly, then all at once. You'll need mobility. You'll need people you trust. You'll need to stay ahead of the collapse as more and more of the planet becomes hostile to human life. As global temperatures rise past 3 degrees, large parts of the world will cross into territory where the human body can no longer cool itself. Wet bulb temperatures make entire regions, once livable, deadly within hours of exposure. If the warming continues unchecked, eventually only a few isolated areas will remain habitable at all. The rest of the planet will suffocate. And even if you make it to year 10, living off-grid, far north, in a community that's adapted to a new reality, the world you've survived won't resemble the one you started in. These doomsday scenarios are terrifying because of how possible they are. They aren't just science fiction anymore. They're rooted in real research, real life patterns, and real concerns raised by scientists today. The question isn't just what if, it's how close are we? And will we live long enough to witness the tipping point? As always, thank you for watching. See you next time.